Swayam Prabha. Digital India. Educated India.
Let us now move ahead and look at solar. So, in the case of solar, solar is much more predictable, and when we talk about solar insolation, we are looking at the direct and the diffuse. So, we have the direct and the diffuse. If you are looking at the direct insolation, this is an instrument which is used to measure the direct beam insolation. This is called the pyrheliometer. This is focused so that it is directly depending on the position of the sun. It will be taking the direct normal beam radiation to the sun, and you have this is the measurement. You also have what is known as a pyranometer, and the pyranometer can be used for measuring diffuse radiation or total. This is a blocking sheet which can be used to block the direct, and then what is measured becomes only the diffuse. If we remove this, then we will get the total insolation which is on a horizontal surface, and that will be the global horizontal insolation. So, the direct plus diffuse will give us the horizontal, and these are the instruments that can be used to measure. Most of the measurement stations will have these type of instruments, and the solar constant ISC, which is incident, is of the order of 1361 watts per meter squared. 1361 watts per meter squared. That is the total amount of solar insolation available per meter squared of surface. When it comes through the atmosphere, some of it gets scattered, some of it comes down at diffuse, some of it gets absorbed, and what we have is what is known as the direct normal irradiance, DNI, and DNI at any point of time, when we talk about the solar photovoltaic, we usually have a standard which is based on 1000 watt per meter square, and we create the characteristics for that insolation. When the insolation is lower, the output would be lower. So, DNI is the flux density of the direct unscattered light from the sun measured on a flat plane perpendicular to the sun's rays. And this DNI that we talk about, which is, so this is DNI is perpendicular to the sun's rays, so that it is you have the normal irradiance which is there, and this flux varies over the day as the sun rises, and there is a peak, and then it goes down in the evening. When we look at the DNI, every hour we can measure the DNI and then make a plot. We can take the aggregate amount of the irradiance over the year, and that is plotted as the annual DNI. So, those are the kind of values which are put. When we look at the spectrum of the solar radiation, if you see this, you will have the sunlight which is there, some of it is absorbed and then it reaches, this is at different wavelengths, and some of it is in the visible range and in the infrared and in the ultraviolet, and all of this is incident onto the device and depending on the characteristic of the device, we have an efficiency which is there, and this is used to convert the energy. So, if you look at now this solar irradiance, these are from a few of the sites which are there in where there have been solar plants, and you can see that in some cases you have this pattern, but because of cloud cover for some hours there is a drop in the irradiance, and this is from a site in Gujarat for a particular day, one of the days you have no cloud cover, and you can see that the generation megawatts follows the classic example of what we expect from a solar PV plant. On another day there is some cloud cover at this point, and then there is a cloudy days. In this one is a cloudy day with number of cloudy hours and disruptions. So these are the kind of things which I told you that in terms of the interruption and the variability which is there in solar. Solar is much more predictable, as we said, that with the different kinds of, you can measure, this is with a different unit, it's kilojoules per hour square meter. Usually we will put it in terms of watts per meter squared, and then we can take watt hour per meter squared, multiply it by the number of hours, and then over the year you will get something like a kilowatt hour per meter squared per year. And this is the global solar irradiance, and you can see this is the direct normal DNI which is there, and you can see the yellow region. These regions are the ones with high DNI. In the Indian context, we have reasonably good DNI across most parts of the country. There is a variation, of course. See, this is the kind of average global solar irradiance, and you can see this is in watts, average in watts per meter squared over the months of December, Jan, Feb, and this is June, July, August. This is again, both of these are from the Global Energy Assessment. In the case of India, you find that most large parts of the country have, most of the country has DNI greater than 1900 kilowatt hour per meter square, and some of these regions, for instance, this is more than 2200, and so this is quite a good DNI. In order to make a calculation, if you look at the total amount of electricity that we require, we can take that electricity, divide it by the DNI that we have, take the efficiency of the cell, and then calculate what is the area that is required. And if, for instance, if you are talking of 500 billion kilowatt hours, we can see that this can be met by installing about 2500 square kilometers, or 50 into 50 kilometers, or 4 smaller squares of 25 kilometers into 25 kilometers. And so, really speaking, this location which has been selected is a location which has the highest insolation in terms of DNI. It's also a location which is a desert and relatively low population density. However, still, you know, getting 50 kilometers into 50 kilometers is difficult. Creating the transmission and distribution line, creating the storage. In actual practice, when we try to get land is always difficult to acquire, and the requirement for land, the requirement for water in terms of the cleaning the panels, and in the case of solar thermal, even as a working fluid, these are some of the problems in terms of the solar penetration. As I told you, for the you can see this is the global horizontal insolation watts per square meter for a particular location of a PV module in the IIT campus, and you can see that the generation actually follows the insolation data. We can also look at the DNI variation over the years, and you can this is for a particular site at Noida, and you can see that every day the DNI goes up and down, but there is a variation within the seasons, and there is a fluctuation. And so this is one of the issues when it comes to solar. But when we look at solar, there are large tracts in the Indian context. We have a significant amount of solar radiation. Most parts of the country have good solar radiation. Most of the solar is happening though mostly in the west and the south. East and northeast relatively have less solar radiation. So we have this situation where when we talked about fossil fuels, it was mostly in the east and a little bit in the center. Most of the solar and the wind is happening more in the west and the south. So there is a sort of regional disparity in terms of the kind of resources which are available. Let us now look at some of the other sources of energy. If we look at tidal, tidal is the renewable energy source where it is not dependent on the sun, but it is actually the moon. So the gravitational effect of the moon on the earth causes the high tide and the low tide. And the principle typically in a tidal situation, of course you can have tidal turbines which are in the stream just like the wind turbines, but in the other case we allow the water to come in at the high tide and then we block it and then we release the water at the low tide. This difference between the high tide and the low tide, that is called the tidal range. That gives us the head for running the turbines, which gives us the power generation. So the power generation happens only at a fraction of the time when we are releasing the water during the low tide, and it will of course be in. So in the case of this kind of data, we will need to have what is the tidal, there will be a daily tide or a semi-diurnal tide, there will be a tidal range between the high tide and low tide, and this has to be mapped. This has been for all locations of the coast, there are ranges of tides which are provided, and this is a tidal range map which is given in the, you can see of course that we are looking at a tidal range of 10 to 20, 10 to 30 meters would be could be cost effective. Again, depending on the location and the kind of things, one can think in terms of. In India, we have not yet built. There is a plan to build, and I am not sure what is the status of that. Off the coast of in the Bay of Bengal, off the coast of Sundarbans, there is a plan to build a tidal plant. There is also a plan at the Gulf of Kutch. The largest tidal plant is the one in France, which is a 240 megawatt Larance, France, which has been operational for decades, and it's also a tourist attraction. There's a recent one which has been built in Korea in the Siwa Lake. It's about 254 megawatts. So tidal, as of now, there is a potential. It's not yet a commercial technology. There are a few projects. They are demonstration projects. They can be near cost effective, but we do not expect them to have a very major role in the future unless there are technology breakthroughs. In addition to tidal, there is also something called the OTEC, or the ocean thermal energy conversion, and this basically is using the principle that the surface of the ocean is much warmer than the water which is there at the depth, and because of this it is possible to have a normal Rankine cycle where we use the temperature, this temperature difference to generate electricity. And the advantage that we have is that we have a large volume of water, and even though the temperature differences are relatively small, in the sense that we are looking at temperature differences of 18 to 20 degrees, even though they are relatively small, because there are large volumes, we can generate a reasonable amount of energy. We had the largest plant being planned off the coast of Tamil Nadu. It was a 1 megawatt power plant, and the problem was that most of the components were tested. However, when it was put in the field, the pipeline, the HDP pipeline, 1.1 kilometer pipeline kept getting ruptured, and because that was not able to be established, that was the project was abandoned. There are a number of this is the most difficult challenge in the sense that it has to be put in the ocean, which is the most adverse and harsh environment. But however, there is a significant potential to do this. In the case of wind also, in many of the countries in Europe, the land for wind is not available, and the plan is now to move offshore. In the case of offshore, we can have, essentially we will have much higher wind speeds, and we can have large wind farms, and that is the way this is going. Offshore is costlier. Again, there are technological challenges, but this has been the way we are going. In the case of wind also, we've gone for larger and larger plants, and now we have a single turbine which can generate of the order of 10 megawatts. So this is in terms of, we've looked at tidal, and we've looked at ocean thermal. And then there are also, we can also look at these ocean currents, and it is possible to use some of these ocean currents in terms of energy generation. The other possibility related to the coast is to have the energy which is available in waves and to harness that. And in order to do that, what happens is that, see, on the surface of the water, because of the wind, we have the waves, and the waves have the crests and troughs, and we have a number of different devices which can be used. You have the oscillating water column, and you have the Edinburgh duck, and you have the pelamis, different kinds of devices which bob up and down, and that movement, reciprocating air is converted into electricity. This has the largest number of patents which are available for wave power. The problem is that this is all distributed. You need to have a way for taking out that power. We need to have a way for taking that power and converting it into electricity, and then evacuating that electricity and connecting it to the shore. So this is again something where we do not, there is a reasonable amount of potential, and this is that you can see in different regions. You can see that the total terawatt hour which we are looking at, exajoules, is about 106 exajoules, very large potential, but cost effective extraction is an issue. There could be breakthroughs, and this could provide reasonable amounts of requirements, especially for islands and coastal regions. So we've looked at tidal, we've looked at OTEC, we've looked at wave. The other source of energy, as we talked about, is the geothermal energy. And in the case of geothermal, as we said, there is that the at the depth, the temperatures are much higher, and then when you look at the water coming in contact with this, we have essentially hot water or steam coming out. There are many natural hot springs where these come out, and these are usually tourist attractions. Here there are many different technologies where we can have an injection well and an extraction well, where you inject water inside and or a working fluid inside, and then you can have an organic Rankine cycle and have power generation. If you have lower temperatures, we can also directly use it for heating, or we can use a vapor absorption refrigeration system, use it for cooling. There are also geothermal heat pumps and geothermal, so you can have ground, from the ground if you take things, the temperatures are 5 degrees, 6 degrees lower, and you can save energy when you are trying to heat or cool a space. So that's again another application. There are many different countries where this is a commercial technology, cost effective, but it needs it will be in areas where there is already the faults and you have the steam emerging at high temperatures. In the case, so this gives you an idea of some of the different countries and the kind of geothermal installed capacity, and you can see Indonesia, Iceland, Philippines, a number of different countries where there is a geothermal capacity, and this is a map showing the geothermal faults. Before we look at that, in the case of India, these are the geothermal provinces, and if you see in the Indian context, around the fault areas, these are the areas where you have the geothermal, but the temperatures, in most of the cases, the temperatures are relatively low. In some cases in the Puga Valley, we are getting temperatures of 200 centigrade, and so this can be used for power generation. There's a pilot being planned at Puga Valley. Many of these other places, you can use it for cooking, you can use it for heating, and we do not expect geothermal to have a very major role in the Indian context, but locally this can provide some of this requirement. The supply curve we talked about supply curve. The supply curve for geothermal with current technology, you can see that we can get of the order of 200 exajoules or 300 exajoules at different kinds of prices, and with new technology, of course, the prices will go down. That's for the supply for geothermal electricity, and this is for supply for geothermal heat. So similar kinds of supply curves are available for many of these, and this is available in the Global Energy Assessment Resource chapter. We come to now another energy source which is in the Indian context quite important. It is biomass. Biomass could be agricultural residues, crop residues, it could be wastes which are there, and cattle dung, and then this biomass, of a variety of such biomass is available. There are many different processes and process routes for conversion of this biomass. When we try to map this biomass, each of these biomass has depending on the ash content and the moisture content, you have a certain energy content of the fuel, and you can see that in all of this has an energy content between, we are talking of between 12 to 19 megajoules per kg. Remember that we were comparing this with when we talk of oil, it's about, we are talking of 40 megajoules, coal is about half of that, but it's a reasonable source. So it's slightly lower than the energy content in coal, but it is something which is abundant, and of course in some cases they already have alternative uses. It's being used, biomass is being used as fodder for cattle, it's being used as a feedstock, it's being used in thatching for houses. So we have to see what about the supply and demand, and we have to also look at, if you're talking of animal dung, we look at how do we collect it, how do we process it, but we can estimate, and all of this, when we look at getting the estimates of this, these are now stocks. So we will have to have distributed ways of making these calculations. When we do these calculations, we would need to look at, for instance, we know in different regions of the country or regions of the world what is the wheat production, the rice production, and based on that, based on the production, we can find out per ton of product how much tons of residues are produced, and we can multiply that. We can take the yield in terms of how much area under plantation, what is the yield, multiply that by the residue ratio, and then we will get the amount of residue, we can get the energy content of the residue. Also, depending on the growing season and the harvesting season, the residues will be available at a particular point of time. So one of the recent controversies and which has been in the news is has been about the pollution in many of our cities, including Delhi, and the problem with the air quality has been blamed on the stubble burning which has happened in Haryana, in Punjab, and the crop residues and the stubble. And it's possible, of course, to gasify it, use it for energy, and we have to work out the things. So this is the kind of potential. So in all of this, you can take the rice, again the quantity of residue, the residue ratio, and the residue energy. So that's how we can calculate the biomass. In the case of biomass, there are different possible processes. There are thermochemical processes where we can look at if it's combustion, just like we have in a power plant, the Rankine cycle power plant. We burn coal and then we get steam, and then we use that steam to run a turbine. In this case, we can take biomass, we can take bagasse, we can take rice husk, we can burn it and generate steam, generate power. The efficiencies are slightly lower than that of a coal based power plant, but it could be also co-fired. You can have coal plus some biomass. And the other route is, instead of combusting it completely, we can gasify it. That means we add less air so that it is partially gasified. It is gasified and you get carbon monoxide and hydrogen, which is the producer gas, and that producer gas then can be used to run an engine, a diesel engine or a dual fuel engine or a dedicated producer gas engine, or we can pressurize it and use it for a gas turbine. Most of our Indian experience has been with atmospheric gasification, and we have been using that gasified output for heating, thermal, or for running an engine and generating power, shaft work. We can also think in terms of using this biomass for pyrolysis and getting liquid fuels. So this is thermochemical. The rates of reaction are higher. These are all chemical reactions. Biochemical is where we let now the microbes do the work for us. In the case of digestion, anaerobic digestion, we get biogas. It settles down and we get biogas, and we also get slurry. And we can use this also for fermentation, get ethanol. You can have oil extraction, and you can have biodiesels and biofuels. In the GEA and in this special report on renewables, you can find all of this again in terms of different biomass feedstocks, different kinds of conversion routes, and different heat outputs in terms of heat to power, heat or power, or liquid fuels or gaseous fuels. So there are many different things which are possible. In the case of biomass, the issues is that if we want to dedicate some land for biomass production, then there is an issue of food versus fuel. And we can, if we, on the other hand, if we just use the resources, the wastes which are coming from the animals or wastes which are coming from the harvest, and then we can look at this has alternative use, and then we can look at the surplus which is there going for energy conversion, and then look at the end use. If we are doing dedicated plantations, there is a food versus fuel, and that is a problem. We need to see, we also need to see if we are getting biofuels, what is the amount of energy that we are putting into creating that biofuel. So in a later lecture, we will talk about net energy analysis, and we will see how this looks. So when we look at biomass plantation with the different kinds of yields, this is the kind of yields which are available in different parts of the world, and this has been given. This has again been classified in terms of a technical potential of biomass. The problem in the case of biomass is that aggregation and creating a number for the country or number for the world is a difficult exercise, and it's subject to many uncertainties. This is a local issue, and we really need to identify locally the supply, demand, and the maps. In the case of bioenergy, this supply curve which has been drawn in the GEA, if you see, this supply curve gives you at different we can go up to 80 exajoules per year at about $6 per gigajoule. Biomass can be reasonably cost effective. There is an issue of, as we said, the use of land, use of water, and we have to look at it in terms of the sustainability. But biomass, bioenergy systems have not been growing at the rate at which PV and wind have been growing. Bioenergy systems have the added advantage that most of the technology and most of the, it generates local employment, and these are some things where we think in the future that there will be much more in terms of potential. In Europe, there have been some estimates of the kind of, from different kinds of, there are different technologies for conversion. There is first generation, second generation, and with genetic engineering we are looking at different kinds of conversion routes. In all of this, we have to look at the overall sustainability in terms of energy as well as other issues in terms of land and water. But this is some of the things which is there. And this is an aggregate supply curve with municipal solid waste, animal waste, crop residues. So if we combine all of this, you can see then this is an image which is there from the Global Energy Assessment, which talks about electricity, heat and primary energy, and talks about the exajoules available. We can clearly see that in the case of renewables, we are not constrained by the potential. There is significant amount of potential. This may be distributed. We have to see how and where we can do it in terms of cost effective methods. When you analyze any particular location, we can find out what are the local resources in terms of renewables, whether it is solar or wind, and then identify for the demand how much you can require. We can then look at the cost effectiveness of such things. One of the key things when we talk of a renewable situation and when we are looking at large scale renewables is that we have to match the supply and the demand. And matching the supply and the demand means that we will look at solar. The solar supply is starting from, let's say, 6 o'clock or 7 o'clock in the morning and going up to 5 or 6 in the evening. When your demand is in the night and we are looking at the commercial load and the lighting load coming in from 6 in the evening till about 10 or 11 in the night, where we have a high demand, we need to then store the energy which is coming in from solar and then use that energy in the night. This involves an additional cost, and the total amount of storage that we have installed for the energy sector is not even 1% of the total energy that we supply. And this is also, there are many different storage options, and this is of course another topic, but when we look at, you can look at the economics of different kinds of storage. It could be large scale storage, it could be distributed storage, and when we talk in terms of storage, large scale storage, it's mostly we are looking at, today the most cost effective large scale storage is the pumped hydro, where we look at hydro having a low reservoir and a high reservoir, and you pump the energy from the low reservoir to the higher reservoir. Even that today, at today's prices, that costs you another 5 rupees per kilowatt hour. So this is going to be an issue when we talk in terms of high renewables. The matching of supply and demand, we try to see, so far in the electricity grid we were looking at thermal and hydro scheduling. Now when you have renewables, we have thermal, hydro, solar, wind scheduling. Mostly today, in order to encourage renewables, when we supply renewables, we consider them as must run. That means when the PV generates, we try to use it. When the wind generates, we try to use it. This will result, as we saw in some cases, in the backing down of thermal power. So when we look at a future demand and we have high renewables, what we do is we take that future demand, subtract from it the renewable share, and then see the net energy which has to be met by the fossil. And this leads to what is known as that California duck curve. So we have to see whether or not the supply system is able to meet that, and this involves So, at the system level, when we talk of high renewable energy penetrations, we have to plan our systems differently. In the GEA as well as in the special report on renewables, there are some supply curves given for renewables, and you can look at this in a little more detail. So, to sum up, we have looked at today the different methods of assessing renewable energy resources. We saw that these resources are distributed, and depending on the type of resource, we would map the distribution of the supply. We would also see how it would vary over the day and the season, whether it is wind, whether it is solar, or it is the tidal, OTEC, or the biomass. We have seen different ways to estimate and look at the potential. Today these renewables are relatively small, but they are going to be an increasing part of our energy mix. And when we look at a particular application, we need to estimate what is the technical potential and the economic potential, and then design our systems for that. With this, we will close our chapter on renewables. We will also now look at what is the situation in terms of materials that we need for the renewable sector. Thank you.